All right, good morning, everybody. My name is Kenny Pritchard. I'm a master's student here at Purdue, and today I'll be talking about a simulation-based study of operational vulnerabilities for SmartHabs. So the research question I'm aiming to address with today's presentation is how we can use the habitat simulator, which we've been developing for several years now, to learn how to respond to hazard events under variable circumstances. And I'll break down that research question into two kind of separate but related objectives. The first is about simulation-based research. It's how we can use that habitat simulator and really take advantage of the kind of emergent behavior, complex interactions, and tight coupling that we've been trying to develop into this platform. And the second part is to understand operational vulnerabilities. And when I say operational vulnerabilities, I'm talking about the changing circumstances that affect the consequences of disruption scenarios that happen throughout the lifetime of a SmartHab. So for that first objective for simulation-based research, we want to understand how we can really take advantage of our platform and how we've designed it. So I want to understand the advantages of that kind of platform with reference to the alternatives. So when you're studying SmartHabs, you could have a really simple simulation that just models kind of one metric, like just pressure in the habitat or something. And that would be easy, and you might get some of the numbers you need, but you miss out on the context and the interactions with other subsystems in the habitat that are really kind of the most important to understand because they're the ones that we might not necessarily understand intuitively. On the other end of things, you could do in situ testing, or the closest we can get to it on Earth, which is analog space habitats. And I was lucky enough to spend 2 weeks at the Mars Desert Research Station down in Utah with an all Purdue crew and perform some research there about space habitats. And there was actually another member of the RETHI team there with me. And that was a really informative experience, and we got a lot of good research done. But while we were there, we were kind of limited by the cost of performing that research, the time we spent there, and the kind of safety concerns that are inherent to having human people performing the research. So we couldn't, for example, simulate a fire within the habitat that we were living in or represent a loss of atmosphere due to a meteorite impact. The second objective was about vulnerabilities. So when I say vulnerability, I'm talking about something that affects the consequences or likelihood of a risk to SmartHab operation. This is a traditional NASA risk matrix on the slide. I'm sure most of you are familiar with it. And you can see how the vulnerability there is shifting the consequence and likelihood of that risk. And because I'm performing these simulations within the habitat simulator, and I want to have solid simulations where we're not randomizing things, we're mostly just studying the consequence of these things and the consequences that that changing severity has on our response strategy. So in order to study this, I broke down the vulnerability of the habitat into 5 kind of digestible factors that we can use to develop further research questions. So I have a larger set of research questions that I've developed for these vulnerability factors on the slide, but in this presentation, I'll just be sharing 2 research questions and a sample of their corresponding simulation sets. So the factors are awareness. This is the ability of the habitat to detect faults and diagnose them. Subsystem availability, which refers to the functionality of components within the habitat and the availability of limited resources. Environmental conditions, which refers to the kind of ambient circumstances inside and outside the habitat. Safety control options, which refers to the set of controls of repair and response actions that we can perform at a given point. And recent events is kind of a catch-all factor that refers to lingering off-nominal conditions from previous events. It could be something like a transition that we initiated purposefully, or it could be another disruption scenario that occurred and has not fully resolved yet. So for this first simulation set, it's going to pertain to the vulnerability factor of awareness. And the question is, how does the level of awareness of the habitat affect the propagation of disruption scenarios? The level of awareness can change with things like whether or not a crew is present in the habitat. And especially when they're not present, it refers to sensor functionality and the fault diagnosis, detection and diagnosis systems. So in order to understand this, we simulate a fire happening in the habitat. The fire is occurring near the power distribution system that gets power to the thermal controller. And in order to represent the awareness, we vary the time until that fire is detected. So across 6 simulations, we vary it here from 1 second up to 151 seconds. And when that fire is detected, the agent will move to extinguish it. And in order to understand the results of these simulations in the habitat simulator, we'll plot the radius of the fire and the temperature within the habitat. This plot shows the radius of the fire across all 6 simulations in the set. You can see at 50 seconds, the fire occurs. It starts at a predefined radius, and then that radius begins to grow linearly. When the agent detects the fire and moves to address it, you can see the radius of the fire decreasing in kind of a stepped decrease there. And when the agent takes longer to detect that fire, it not only grows to a larger radius, but it also takes longer for the agent to extinguish it. We can observe the impacts of this fire radius in the temperature in the interior environment. So in this plot, you can see labeled again at 50 seconds when the fire begins to spread. The temperature in the habitat grows very gradually at first because of the heat being put off by the fire, while the thermal control system will attempt to cool the habitat and counteract that. As the agent takes longer and longer to detect the fire, the temperature grows to higher points, and you can see it getting out of the upper limit of the dormant safe range that we've marked on the plot there. And eventually, when that fire grows to a certain radius, it reaches the power distribution systems, and this causes damage to the power distribution to the thermal control system, which means that thermal control isn't fully counteracting the heat put off by that fire anymore, and the slope of that temperature plot is going to pitch up, and it's going to grow even more quickly, even farther into the unsafe range, and take even longer to be restored to that set point when the systems are all repaired. The significance of the simulations that I just shared there are that we can see the context that the habitat simulator provides and the kind of coupling between subsystems. So you have damage to the power, which then causes an inability of the unequal system, the thermal control, to function properly, which then causes a further unsafe state within the interior environment. You could use simulations like this with the proper inputs to make the call, for example, whether to abort the mission or attempt to make the repair when a fire is detected. The second simulation set will refer to the vulnerability factor of environmental conditions, and we'll look at how we can change our response to disruptions of varying severity. In order to represent varying severity, we'll use a meteorite impact disruption scenario, and we'll change the hole size that this meteorite impact is going to cause in the structure of the habitat dome. And we're also going to simulate two separate repair strategies here. We have first repairing the pressure control system that meteorite is going to impact, or first repairing the structural hole that the meteorite causes. On the first plot here, we see the pressure of the interior environment. And in this set of simulations, the pressure control system, which is part of the ECLIS, is being repaired first. So you see the impact happening of the meteorite. The pressure begins to drop very quickly. And depending on the hole size, it may drop outside of the safe range of the habitat. And then in the simulation set, like I said, first the pressure control system is repaired. So when that pressure control is repaired, it's going to attempt to compensate and sort of feed the leak and counteract the amount of pressure leaking out of the habitat. And that'll get most of these simulations to sort of equilibrium point between the pressure leaking out and the pressure being generated by the pressure control. And the habitat will be stable there for some time until the hole is fully repaired and the set point is restored. When we repair the hole first, we see a different behavior. The pressure control system is damaged, so it can't fully restore the habitat to the set point, even after the hole is repaired, but it does maintain it at a stable, semi-stable level until the pressure control system is eventually repaired around 700 seconds and the set point's restored. So what's interesting in this simulation set is that the kind of intuitive behavior or expectation is to repair the hole first because that's what's causing the loss of pressure. But for that really small hole radius there and radii smaller than that, we could see that might be better, in fact, to repair the pressure control system first because you restore the set point, you spend longer away from that set point, and you don't actually dip outside of the safe range. So we can use this to understand the environmental control vulnerability factor and really see that the same disruption scenario, I say same in quotation marks because we're changing the severity level, can propagate very differently depending on that severity level and the environmental conditions. In order to understand how we can prioritize in repair situations like this, we need a database of potential outcomes and more risk assessment associated with these scenarios. The lessons learned overall of simulation sets like this is that we can induce kind of emergent complex behaviors into the SmartHab with the habitat simulator, which gives us confidence in simulations like Jackie's and Rashi's that were just shared, where we form a more structured approach into the simulation and design process for the habitat. We can use context, quantification, and a better understanding of how the initial conditions affect response planning to enable data-informed decisions early in the design process with the habitat simulator.